You see a problem that involves multiplying and dividing complex numbers, consider using the exponential form. This is because multiplying two complex numbers with a magnitude of 1 means that you're adding the angles. In the numerator here, we're multiplying by I. In exponential form, that's e to the power of pi over 2 times I. So I times a complex number z with an angle of alpha means we're adding pi over 2 to that starting angle and rotating it counterclockwise. Conjugates are also easier in exponential form. It's just the negative of the original angle. So our expression here on the right, iz over the conjugate of z, when we substitute in and use our property of exponents, we're going to subtract a negative alpha. This gives us 2 alpha plus pi over 2. In the problem statement, we have that our starting complex number has a magnitude of 1. Let's say its starting angle is alpha 1. This is on the unit circle. And when we apply this transformation, we're not changing the magnitude, only the angle. So z1 means we're going to take I times z0 and divide by the conjugate of z0. And our angle changes to 2 times alpha 0 plus pi over 2. For convenience, since our magnitude isn't changing, we'll just focus on the angles and we'll let alpha 1 be 2 alpha 0 plus pi over 2. This is true for every other complex number in our sequence. We're going to take 2 times the previous angle and add pi over 2. So we'll substitute for alpha 1 here and add pi over 2. I'll write this as 2 squared times alpha 0. Then we have a pi and a pi over 2. This is 3 pi over 2. On the unit circle, 3 pi over 2 takes you 3/4 of the way around, but that's equivalent to going in the opposite direction by negative pi over 2. So we have alpha 2 is 2 squared alpha 0, and then I'll write minus pi over 2. We'll do this again for alpha 3, 2 times alpha 2, and then we add pi over 2. And we'll substitute. We have 2 cubed alpha 0 minus pi plus pi over 2. Here we see our pattern. We'll do it one more time. And yeah, we get the same thing. So for our 2005th term, we'll take 2 to the power of 2005. And in the problem statement, we want this last term to be equal to 1. That's over here on the unit circle, where our angle is equal to 0 or some multiple of 2 pi. We'll write that as 2k pi, and we'll substitute this expression. Let's solve for alpha 0 and divide by this coefficient and simplify these terms. This second fraction is a constant, so as k varies, this first term is the only thing that changes. So let's let beta 0 just be this first angle. As k varies, our starting angle alpha 0 varies, giving us multiple solutions. To see how many solutions there are, let's start with k equals 0. This gives us beta 0 is also equal to 0, which means our starting angle is just this angle over here. If k is equal to 2 to the power of 2005, then beta 0 gives us that number in the numerator and 2 to the 2004 in the denominator. All of these are going to cancel except for one last 2, so that's 2 times pi. On the unit circle, that's equivalent to 0, which is the same solution we had when k was equal to 0. And for larger values of k, we're going to be repeating the same angles that we had for smaller values of k. So our unique solutions come from k starting with 0, 1, and so on, up to a number that is 1 less than 2 to the power of 2005. Counting these, the number of solutions in k is 2 to the power of 2005, which is option E. If you'd like me to solve any math contest problems, please leave them in the comments.